welcome our third speaker, Daqian. Daqian is a PhD student in the Department of Computer Science at University of Hong Kong, where he is advised by Professor Yiming. His research interests expand computer system, networking, programming language, and formal methods. His current work explored how to use neurosymbolic methods to explore behavior of network hardware and systems such as network switch and cloud infrastructure. And his the name of his work is Towards Various Switch Behavior Modeling. So let's welcome Daqian, please.
Okay, so this is Daqian from the University of Hong Kong. Today I'll present our first step towards automatically learning a behavior model for network switch. This is a joint work between HKU and Microsoft Research. So let's begin with the operational problem. So consider a network engineer investigating unexpected behavior in a production switch. The cause may be a hardware or software bugs, a recently introduced feature, or an interaction omitted from the menu. From the operator's perspective, a fixed function switch is a black box. We can install control plane rules, send an ingress packet, and observe the results. But the internal decision process remains hidden. The behavior space also grows rapidly with packets, rules, and feature interactions. A targeted experiment may explain one incident, but it does not provide a reusable account or how the device will behave after the configuration or firmware changes. This is a gap that motivates our work. And we first consider what we can learn from vendor documentations. So vendor documentation is an important source of prior knowledge. It identifies supported features and often gives a coarse view of pipeline order. However, the yellow region illustrates a possible gap between the written description and actual device behavior. The documentation may be out of date or omit details that matters only when features interact, such as precedence, table misses, or header rewriting. It is also written in prose, so it cannot directly predict the output for a particular packet and rule set. We therefore use documentation to initialize the model, but not as executable ground truths. So ground truth observations must come from hardware. And to obtain these observations, we prompt the switch directly. We install rules in the packet and record whether the packet is forwarded or dropped, the selected port, and any header changes. So each prompt gives a reliable observation of the current device. The limitation here is coverage. A query represents only one point in a computatorial space, while raw input-output pairs do not reveal which stage caused the outcome. Large-scale probing also consumes hardware time. Hardware observations are essential for validation, but by themselves, they remain isolated examples rather than interpretable model. So we therefore need an executable model that connects documentation with observed behavior. So we argue that the missing part here is an executable behavior model that combines these sources. Documentation supplies an initial structure, and observations align the structure with the device. The model can be used before deployment to check a configuration or after an incident to identify where packet behavior diverged. It also provides a common basis for comparing device or firmware versions. In this work, we focus on functional packet processing, which is whether a single packet is forwarded or dropped, which ingress is chosen, and how the headers are rewritten. Queuing and throughput are outside the current scope. Our objective is a useful semantic model of forwarding behavior, rather than a complete digital twin. So Lumen is our first approach to learn this model. This slide summarizes the Lumen workflow. We begin with vendor documentation and the controller API. So semantic parsing converts them into a preliminary scaffold that includes candidate features and their dependencies. Lumen then grows an executable model, one observed slice at a time. After adding a slice, it generates tests for newly reachable behavior and runs the same cases on the switch. Any disagreement is returned as a counterexample, and the slice is revised before synthesis continues. This loop avoids synthesizing the entire switch in one step. Once the broad model is available, operational traces can expose behavior missing by model-generated tasks. Lumen uses those traces to localize the remaining discrepancy and apply a bounded repair. The result is a model shaped by documentation, but repeatedly checked against hardware. And I will describe the stage in more detail, beginning with semantic parsing. So the first stage extracts a constraint synthesis problem from two complementary sources. When the documentation provides an approximate pipeline structure. So in this example, it suggests that L2 lookup precedes IPv4 routing and the echo. The controller API provides a more concrete description of available match fields, actions, and parameters. So Lumen uses an LLM to interpret the props, but treats the result as a candidate rather than a fact. It normalizes vendor-specific names and combines the extract information with the API schema. The output is the match action specifications and dependency graph showing on the slides. So this constraint substantially reduces the space that subsequent synthesis must explore. And with this scaffold, Lumen can begin incremental synthesis. The central design choice in incremental synthesis is the unit of growth. Adding a very small component, such as a parser rule, may not change any externally visible output, so the hardware cannot tell us whether it is correct. Lumen instead adds a small list of observable slides, which is enough parsing and match action logic to create a new packet outcome. In this example, the model first captures coarse control flow, then adds L2 lookup, followed by L3 forwarding after its dependency is available. Each increment is immediately executable and can be tested on the switch. This keeps the synthesis problem manageable and, when a discrepancy appears, limits the likely cost to the newly added slice or its boundary with the existing model. So each slice is aligned with its devices before the model grows further. And after a slice is integrated, Lumen symbolically executed the update model. An SFTP solver generates packets and rules configurations that exercise the new passes, and the same cases are replayed on the hardware. If their outputs differ, the mismatch becomes a counterexample. Because the earlier model has already been checked, Lumen can localize the discrepancy to the new slice or its interaction with existing behavior, then refine it before continuing. We call this model-centric alignment because the current hypothesis determines which test to run. And the preliminary evaluation used tailored switch.p4, which is a well-used P4 software switch, while exposing only the black box interface assumed by Lumen. Here we show an application study. As the model pipeline expands from L2 to include L3, echo, and MPLS, which is pipeline complexity we shown in the figure, the full system remains at 100% success in this experiment. Removing alignments and incremental reduce final success to about 40 to 60%. With both removed, success is around 10%. The results suggest that the different mechanism we introduced in our work can be a promising solution for future synthesis tasks. And follows one complete run. So the bars here report the number of test cases, and the black lines show the pass rates. During runs, Lumen adds features incrementally. We can see some short drops in pass rates are corrected near the point where each feature is introduced. This drop exposes a residual semantic gap in the model. And after repair, the pass rate returns to nearly 100%. Our current prototype uses a lightweight repair heuristic. Here we just simply prompt a coding agent to do the repair. And we believe that improving the localization and constraint repair is an important next step. And overall, we think that this result suggests that a fixed function switch can be modeled by growing an executable hypothesis and repeatedly aligning it with the hardware behavior. Okay, that's the end of my presentation. I'm ready to take questions.
Thank you. Any questions? Please.
Thank you. Thank you for the interesting work. I got two questions. First is, do you have any thoughts on how do you have an estimate or measure of how, I would say, the coverage, right? Because I assume input space big enough that you can exhaust it. So I don't know if you have an idea of how you measure how confident it is with the model or how much coverage it is. And second is how the emissions could be used to analyze spatial behavior.
Yeah. So firstly, I'm prepared to answer the first question. So the output of Lumen is actually a data plane emulator. And we think that for each emulator, you do not like claim the completeness or soundness or coverage, but we can do measure the fidelity, right? So Lumen is like a modeling of the data plane behavior. And we can like assume that we have a finite behavior space like L2, L3, this forwarding behavior, right? And then we can like create a enumeration space, and we have a test suite, and you can like metric the success rate on this test suite. So you do have a bounded space, right? So for the second question, so could you like repeat it?
Yeah, the question is sometimes the switch behavior also depends on the space. For example, the flow has passed through it.
Yeah.
Must have different state.
Yeah.
But then how do you validate that? You have to replay the whole flow, but validate and test rate.
Yeah, that's a really good question. It's also related to like the how many behavior you can model, right? So we think that for current stage, we don't have that strong like search power, right, capability. So we're just focusing on the single packet behavior, like you inject the packet and it is dropped or rewritten, and we also can have some witness about the counter or something like point to CPU, this kind of behavior. Yeah. So we don't cover flow and other stateful behavior in our work, but we think we can maybe make it in the future. Yeah.
Yeah. Thank you.
Thank you. Any more questions? If no more questions, let's welcome our fourth speaker, Ori Renton-Stretch. Ori is an associate professor at the Daqian Israel Institute of Technology. He is interested in the design of network algorithms with a recent focus on networks for ML. He is always curious about collaborations with highly motivated students from other universities. So let's welcome Ori.